All right, so with that being said, let's start looking through this textbook. And so a lot of this stuff is just, there's introductions and things like that. And the first section sort of motivates this textbook and gives a few examples of very common places. Like these examples, you'll see these pop up in tons of different textbooks. And you'll see some of these examples pop up like this like this data set you see used very frequently. So these are very common examples that help motivate why data science is useful, and they also show a couple of different types of problems that data science is really good for solving. And so that is this section, and there's not a lot of calculations or anything, so I'll just let you read that on your own. Now when we get here and we start talking about supervised learning, here is where we start getting into some calculations, and so this is where I'm going to help fill in some of the gaps. So a lot of this at the beginning is just definitions, which will make a lot more sense once we start looking at examples. I do want to talk about this though, because just in general in math, notation is really tricky. It's tough to really come up with really good notation to use. I think there's a partial differential equation textbook by a professor whose last name is Evans, and I forget his first name, but I remember in his textbook, in the intro, he says it's something along the line of notation is a nightmare, and it is really tricky. And so I really want to take some time to flesh out and understand the notation that's being used in this textbook. So basically, it's not easy for me to have an underline or to have bold face when I'm just writing with my pen here. So I will just underline a variable if I want it to be in bold text. So typically if we have a matrix X here, so this represents an n by p matrix. So this is, let's see, if we're using matrix notation here, it is an n by p matrix. And so in terms of how this relates to this other to these other notations, so we have these lowercase xi, and these are vectors of length p. And so the way that this works is each of these vectors is a row in this matrix bold X. So let's write out what this looks like. So this would be lowercase x1 all the way down to lowercase x capital N, because there are n rows. And let's see here. There's also the tricky thing where whenever we write a vector, we assume that the vector is sort of written as a column matrix. So this vector xi is a p vector, so it's a vector with p elements, and those elements can be written in a matrix of size p by 1. So because these lowercase xi's, because these are rows in this matrix, we technically want to take the transpose here. And I feel like using this transpose sort of like clutters up the notation a bit. I feel like oftentimes by looking at the context you can figure out whether a vector should be a row vector or a column vector. But some of the calculations later on get a little tricky. So just to be super consistent, let's just do this. And so I'm going to put these lines here to sort of represent that each of these xi's, or xi transposes, each of these is a row. So it's a row of size p. No, yes, it is a row of length p, and there are capital N of them. And let's see here. Right, so this is lowercase xi. Now also we have uppercase xi's, I believe, as well, that get included at some point here. Yeah, I think that's what this is. So in general, vectors will not be bold except when they have n components. So basically what this is saying is that what we could also use is, so lowercase bold xj consists of all the observation on variable capital Xj. So what this is saying is that each of these bolded, like we have a bold x1, and here we don't take the transpose because remember vectors are like column vectors. So they're vertical. They have so this is an n vector, so it has n entries, and so though it has n rows and one column. So it's just a column here, and then this goes all the way over to lowercase bolded xn, and this is also a column, and then these together form this matrix. So these are two different ways of writing the matrix capital X bold. One of these ways of writing it specifies the row vectors, and these are written using lowercase x's, and one way of writing it specifies the columns, and these column vectors are written using bolded lowercase vectors. And we also let's see here, we also have if n equals 1, then we have this vector capital X, and it's written in such a way that when you take the transpose, you get this vector, which is x1 all the way up through xp, and these are all capitalized. So basically the way that we can think of this is when we have capital X i's or capital X j's, like right here, we have capital XJ. These capital X j's, basically these are referring to the entries of a single row of data. Because this notation is a little abstract. We want to tie this back into our understanding of like data sets, because ultimately, like when we start programming, we're going to be programming with data sets. And so we want to have in mind what these variables are representing. So capital X bold is generally representing some sort of data table, some sort of table of data that you have. And each row represents an observation or a data point. And each column represents one of the features of the data set. So I want to see if I can come up with a quick example here. I might not be able to come up with an example very quickly. But yeah, so if we're looking at email spam, then if we have a table of data, each row could be a particular email, and then each column could be some characteristic of the email, some description of that email, like maybe it's like the length of the email, the recipient, the sender, all of these pieces of information. And so that's the difference between the rows and the columns, and that's important for taking these matrices and sort of relating them to the data sets that we see in the real world. It's also worth noting here, so we have these lowercase x's and these uppercase x's, and it's sort of a little vague to me. So we will typically denote an input variable by the symbol x, and its components can be accessed by subscripts xj. So it sort of sounds as if these capital Xj's are sometimes referring to like almost like if you're looking at a table, they could almost be like referring to the column headings, like they're just identifying like what feature of the data set you're looking at, what column of the data set you're looking at. And so it's sort of a little vague to me because sometimes they'll use uppercase X's seemingly to refer to like a particular like point of data, but then if you have a collection of data points, then you switch to lowercase. So again, notation is really tricky, but we'll do our best to try to understand it, and it will make sense as we work with these things more. Okay, so let's start getting into linear models, because this is where we start seeing equations, which means that we have potentially more work to do. So this tells us about how to predict the output. So again, so each of these betas is just like a value, and this shows how to take these. Now here, each of these capital Xj's is just a number. And so that's how this calculation would work out. This also shows you how you can make this a little more complicated. If y is a vector rather than just a value. But then I want to move down here a little bit to where we start talking about the residual sum of squares. And so it's given by this equation. So the residual sum of squares, basically what this is doing is this is taking like the distance between the actual so here the distance between the actual value and what the model would predict, and then taking those distances, squaring them, summing them up to give sort of like a total difference between what the model predicts and what's actual. And so we have this notation, but we want to do some calculations on it to better understand it, so we can write it like this. So here's the first thing, is let's actually understand this, why this works out better. So what is each of these y minus capital X beta? Again, I'm using the underlines to denote uppercase. So this, so capital Y or lowercase y bolded is a column vector, and it has capital N components, and it's going to be y1 through yn. So let's start writing that out. So I'm actually going to, I'm going to zoom in a little bit. I think I'm going to end up doing a bit of zooming through this as we go through this. So it's going to be y1. I'm going to do this over here, equals y1 all the way down to y capital N. But then we also want to subtract capital X bolded times beta. So if we remember, this is a n by p matrix being multiplied by a p by 1 column vector. And so that is going to give us a capital N by 1 column vector, which it must, because that's the same dimensions as this. And if you're adding and subtracting matrices or column vectors, like they have to have the same dimensions. Okay, so what is the first entry of this going to look like? Well, you get the first entry by taking the first row of this matrix and multiplying and taking the dot product between that and this column vector, because that's just the rules of matrix multiplication. that is not what I want. So let's see. So this is minus, and right, so we are taking, remember what we talked about previously, if I can find it even actually. Yeah, it's all the way up here, that's right. Okay, so remember the rows are lowercase x I transpose. So this first row is going to be lowercase x 1 transpose. So it's going to be lowercase x 1 transpose times beta. And this is, of course, here we are doing this is a n by 1 row. No. This is a 1 by p row vector times a p by 1 column vector. And so this is basically the same as taking the dot product. And so this will just give us a single number at the end. Let's enter these. And so this is going to be x capital N transpose beta. All right, so we're going to end up with this. And so basically, if you take this, so this is a column vector. If you take this column vector and transpose it, you just get it as a row vector. And so you take this row vector and you multiply it by itself as a column vector. And so then what you do is you take the first entry of this row vector times the first entry of this column vector, and then you add the second entry of this row vector times the second entry of this column vector, and you just add all of those up. But these are the same, this is the same vector, it's just the only difference is that one is transposed. So the first entry of here and the first entry of here are both going to be y1 minus this thing. So when you multiply that by itself, you're going to get y1 minus x1 transpose beta squared. And you're going to get that thing squared for every single entry in this vector. And then you just add them all up at the end. And that's precisely what this is. If we look at it, you take each yi minus xi transpose beta, you square it, and then you add them all up together. And that's exactly what this is doing. So that's why this works out. Okay, so now what we want to do is, I wish it was easier to sort of switch between zooming in and zooming out and between writing. Okay, so what we want to do is we have this formula for the residual sum of squares, given a particular guess beta for what the optimal beta is going to be that minimizes this equation. Because what we're trying to do is we're trying to minimize this value, because when we minimize this value, that means that our model is as close as it can possibly get to each of the actual data points. All right, so we have a function and we want to minimize it by changing this input variable. So if you remember from calculus, what you need to do is you need to take the derivative with respect to this input variable and find where that derivative is 0. And that's going to give you your critical points. And so those are the points that could possibly be your minimums. Just again to sort of review this a little bit from calculus. So if you have a function here that, let's say you have this function, nope, oh well. Y equals x squared. This is the x-axis, this is the y-axis. If you have this function y equals x squared, it should be touching the x-axis, but it is not. The way you find the minimum, so the minimum of this function, I should draw it like this. Here we go. The minimum is going to occur where the derivative is 0, and that is right here. And the way you find that is you just take the derivative of this, y equals x squared, derivative with respect to x is 2x, and that equals 0 precisely when x equals 0. Okay, so you found your critical point. Now, something I'll mention now as well is that this isn't all that you need to do, because you could have something like this where the derivative, so I don't remember a good way to write this at the moment. This might be like negative square root x or something, I don't know. But it could be the case that you have a critical point where the derivative is 0, but it's not actually a minimum. It could be like this, or it could even be a maximum. It could look like this as well. So in order to make sure that it is actually a minimum, you need to take the second derivative. So first of all, let's write y prime equals 2x. So we know that y prime equals 0 here when x equals 0. But then the second derivative, y double prime, this is equal to 2, and 2 is positive, and that means that this function is concave upwards. And so that means, I think in calculus it's called concave up, and later on in like more advanced math it's called convex, but basically it's just bold upwards. And that's the case because the second derivative is greater than 0, and so that's how you know that this critical point is a minimum. So we need to do that here.